Okay, so we talked about arithmetic sequences and what the common difference was and how an arithmetic sequence needs to be adding or subtracting the same amount on every time. And we said that arithmetic sequences are linear patterns. They would follow a linear relationship. So we're going to look at each of these different examples here, and we're going to try and determine, is the relationship linear, meaning does it follow a line, or the pattern that a line would make? And we might have some sort of extending question off of that. So this first one here says the population of a town doubles every 3 years. The population in 1997 was 12. So the first question, is the relationship linear? And what we can think about is, are we adding or subtracting on the same amount to the population every year? And if you think about it here, doubles doesn't mean adding or subtracting the same amount. That means multiplying the same amount. That's actually something different called a geometric sequence. So this actually would not be a linear relationship because it's not increasing or decreasing by the same amount every time. I'll show you just a little bit more specifically here in a second. So now we're going to find the population in the year 2006. So we've got the population in 1997, and we know that the population then was 12. And what's going to happen is this population is going to double every 3 years. So the next time the population we will have a clear indication of what it would be in the year 2000. That's 3 years later. And in the year 2000, the population is going to double and be 24. Notice that that's an increase of 12. So if it were arithmetic, it should increase by the same amount every time. And now if we go to 2003, again, the population should double, so this would be 48. And again, that's now a difference of 24. So right there we can tell this is not linear, it's not arithmetic. So if you couldn't figure that out from just looking at it at the beginning, you can write the pattern and still see that this is not linear. And then finally, 2006, if we double 48, we should get 96. So that would be the population in the year 2006. So 96 people would be living in that town. Okay? So that would be an example of a nonlinear pattern. Let's try another one here. A baby blue whale, when born, is about 23 feet long and weighs about 5,500 pounds. Baby blue whale calves grow about 200 pounds per day. That's a pretty big baby, and that's a pretty fast growth rate for the baby. So again, we'll look at this. Is the relationship here linear? So if our baby blue whale is growing about 200 pounds per day, that means each day you're adding on the same amount. You're adding on 200 more pounds. So is this relationship linear? Sure. That's going to be a linear relationship because it's adding on 200 pounds every day. We're not multiplying 200 times their weight. We're adding the same amount on. And then next one says, find out how much a blue whale calf weighs after 25 days. So if we think about this, we've got a starting weight of the blue whale calf, which is 5,500 pounds. And what I'm going to do is I'm going to add on how much weight it increases over that period of time. If it's going 200 pounds per day for 25 days, if I multiply 200 times 25, that'll tell me how much weight it's gained after birth for those first 25 days. So we'll go ahead and calculate here. If I take my 200 times my 25, and then I add this all on, so this will give me 5,000 here. And if I add this on, I should be coming up with 10,500 pounds. Again, that's a pretty big baby. So 10,500 pounds would be the weight of that blue whale calf after 25 days. Again, it's a linear relationship because we're adding on the same amount each day. Okay, we could also have a graph and maybe be asked if it's a linear or nonlinear relationship. So if we look at this graph, it has a number of months throughout the year. And we have, let's say, 4 rabbits in a habitat in May, and this would be the number of rabbits, over that period of time. So, first off, is the relationship linear? There's a very, very good reason why this graph is not going to be a linear relationship. And if you think about what the word linear means, well, it's got to be the shape of a line. If this isn't a straight line, it's not linear. So right here, we know that's no. There might be a portion of the graph that appears to be linear, maybe in this area that kind of looks like a line, but the graph itself is not linear. It's making some little, curve shape there. So explain what is happening in the graph, and I'll probably just talk about this here. You know, there's a whole bunch of different interpretations you could have. You know, if this habitat has a limited amount of space, so imagine that we've got like a box here for our rabbits, or an enclosed cage. You know, and I'm not a very good artist, so I'll do my best here. Let's imagine that this is my rabbit, and here's the ears. We'll give him a fluffy little tail, and he's got some stumpy little legs here. If this is my rabbit, you know, if the rabbits were to keep reproducing in here without kind of any limitations, eventually you're going to have rabbits just kind of overflowing this box. You know, if this curve doesn't come back like it does and start leveling out. So eventually the rabbits are going to run out of space or possibly food, so the population won't be able to, you know, rise above a certain point. Another possibility could be that, you know, this could be the end of breeding season, where the rabbits are no longer reproducing, so the population is going to level off at this point. Okay, so again, there's a couple different reasons why you know, this might be occurring in the graph, where the growth of the rabbit population is decreasing. Okay, or excuse me, not decreasing but leveling off. And that's just an introduction to patterns and how you can apply them in the real world, how to tell if something is linear or not linear. We said that linear graphs should look like lines, and they should be adding or subtracting the same amount every time. We said that nonlinear graphs are not adding or subtracting the same amount every time, and they don't look like lines. And again, that is just some applications of arithmetic sequences.